This video is about solving conditional probability problems using tree diagrams. So tree diagrams are a second key way of visualizing a probability experiment. So we've looked at Venn diagrams, now it's tree diagrams. They are good at representing conditional probabilities. Okay, so what we have normally is events at the end of each branch, we say. So these A, B, B dash, A dash are all events. And then each of the branch is labeled with the probability of that event happening. So for example, the first one is P of A. And that would be the probability that A does not happen. Okay, and each branch adds up to 1. So this would add up to 1. Okay, the second branch, we look at A. This is probability of B given A, because A has already happened and then B has happened. So this is probability of B given A. And the second branch on the second level will be probability of not B given A, because A has already happened, probability of not B happening after A has happened, so on. Okay, so that is how we label tree diagrams. Okay, if A and B are independent, then probability of A is equal to probability of A times probability of B. So all you're doing is when you're going down the branch, so if you're traveling in this direction, because if A and B are independent, then you can just do probability of A times probability of B to get probability of A intersect B. In a similar way, probability of A intersect not B is probability of A times probability of not B. And probability of A not A intersect B is probability of not A times probability of B. And probability of not A intersect not B is probability of not A times probability of not B. And all this is true only if A and B are independent events. And the key thing is only one branch occurs. Therefore, each of the branches are mutually exclusive. So if there is more than one combination to calculate the probability, you have to work each one out and then add it all together because they are mutually exclusive. So let's look at some examples. So a bag contains 24 balls, 18 red and 6 green. 2 balls are taken without replacement. So that's important because if we were replacing it, the probabilities won't change. But because we're not replacing it, the probabilities will change as we go down the event. Complete the tree diagram and find the missing probabilities. So probability of red is equal to 18 out of 24. I'm not going to simplify because you don't get any extra mark for simplifying. Green is 6 out of 24. Now, the probability of picking ball 2, which is red, because we've already picked a red for the first branch, then this will be 17, one less. So 17 out of 23, because there's 23 now in total, 17 of them red. We didn't pick a green, so that would be 6 out of 23, still 6. If, however, we picked green as the first ball, then that means the number of reds would not change, which is 18, but the number in total will be 23. And if we pick green as the first ball, the second ball of green will be 5, because there's one less green ball out of 23. So if we want to work out each probability individually, because the event picking the first ball and picking the second ball are independent, we can multiply probabilities together to get the probability of all the combinations. So probability of a red will be 18 out of 24 times 17 over 23. If you put that into your calculator, you get 51 out of 92. Probability of red-green will be 18 out of 24 times 6 out of 23, which gives me 18 out of 92. Probability of green-red is 6 over 24 times 18 over 23, which gives me 18 out of 92. And probability of green-green is 6 over 24 times 5 over 23. When simplified, gives us 5 out of 92. Now you can see if you do 51, add 18, add 5, you do end up with 92. So it's 92 out of 92. All the probabilities, it does add up to 1. So what is the probability that both balls are green? So that means it's probability of green. We already worked that out. It's just 5 out of 92. What is the probability that at least one ball is green? at least one ball is green means one green ball or two green ball. So that means the combinations that we need to look at is probability of green and then red plus probability, because they're mutually exclusive event, probability of red and then green, which is different to green red, and probability of green, because at least one ball is green means both of them can also be green. So green red is 18 out of 92, plus red green is 18 out of 92, plus green green is 5 out of 92, which gives us a total of 41 out of 92. This can rewrite this as fractions properly. So it's 5 out of 92 here. This one was 18 out of 92, 18 out of 92 plus 5 out of 92. Okay, next question. At its 40,000 miles service, the probability of a car needing new brake pads is 0.3. So I would do brake pads is 0.3. No brake pads, so brake pad dash is equal to 1 take away 0.3, which is 0.7. If it does not need brake pads, the probability of it also needing, if it does need brake pads, the probability of it also needing new discs is 0.7. So new disc is 0.7, which means it doesn't need a disc is 1 take away 0.7, which is 0.3. If not, the probability of needing new disc is 0.1. So if it doesn't need a brake pad, the probability of getting a new disc is 0.1, which means not disc is 0.9, because it has to each section has to add up to 1. So that has to add up to 1, that has to add up to 1, that has to add up 1. Okay, given that the car needs discs, find the probability that it also needed new brake pads. So probability of brake pad given that it already has new discs. So probability of brake pad, because it's given first that it's new disc, so this has to be the second part, and needed new brake pads. So brake pad given disc is equal to, using the conditional probability formula, is brake pad intersect disc over probability of disc, which is the same thing as probability of brake pad intersect disc. And the way that you can get probability of disc is probability of brake pad and then disc, or plus probability of not a brake pad intersect disc. So there's two different options for probability of disc, which means if I'm working out probability of brake pad and new disc is 0.3 times 0.7, all over brake pad and disc is 0.3 times 0.7, plus not brake pad is 0.7 times disc, which is 0.1. When we put this into our calculator, we end up getting 0.75. Next question, the probability of Ganesh oversleeping is 0.2. So let's say oversleeping is 0.2. Not oversleeping would be then 1 take away 0.2, which is 0.8. If he oversleeps, he has a 0.8 chance of being late. So late and not late. So 0.8 chance, which means not late would be 1 take away 0.8, which is 0.2. If he wakes up on time, so which means he doesn't oversleep, then the chance of him being late is only 0.05, which means not late would be 1 take away 0.05, which is 0.95. Given that Ganesh is late for work one day, find the probability that he overslept. So this is probability of overslept given that he is late, which is probability of overslept intersect late over probability of late using the conditional probability formula, which is probability of overslept and late. And the two combinations where you can get probability of late is probability of oversleeping and late plus probability of not oversleeping and late, which is, the first one would be oversleep and late would be 0.2 times 0.8. All over oversleep and late is 0.2 times 0.8 plus not oversleeping and late is 0.8 times 0.05, which gives me a value of 0.8 in my calculator. Next question. A bag of 24 chocolates contains 10 dark and 14 milk chocolate. Linda chooses a chocolate at random and eats it, followed by another one. So that means we're not replacing it. So it's a conditional probability. The probabilities are going to change. Draw a tree diagram to represent this data, to represent this information. So we've got dark chocolate and milk chocolate. Dark chocolate is 10 out of 24. Milk chocolate is 14 out of 24. Then the second chocolate that she takes can be dark or milk. If she takes the dark already, then it's going to be 9 out of 23. The milk chocolate numbers would not have changed, so it's 14 out of 23. And then if she takes the milk chocolate first, then the dark chocolate would not have changed, so it would be 10 out of 23. And the milk chocolate would have gone down by 1, so it's 13 out of 23. Okay, part B. Find the probability that Linda eats 2 dark chocolates. So probability of dark and dark. So it's probability of D times by probability of second D, which is 10 out of 24 times 9 out of 23, which gives us a value of 15 out of 92. See, 1 dark and 1 milk chocolate. So that means there's 2 different ways you can get that. It's probability of dark and milk plus probability of milk and then dark. So dark and milk is 10 out of 24 times milk, which is 14 out of 23, plus milk, which is 14 out of 24 times 10 out of 23. If I put this into our calculator, we end up getting 35 over 69. Okay, 2 dark chocolates, given that she eats at least 1 dark chocolate. So that means D is probability of dark and dark, given that she's already had a dark chocolate, at least 1 dark chocolate. So that means we end up getting probability of dark, dark intersect dark over probability of D. Now that means at the top, because it's dark, dark, and she has at least 1, there's only 1 combination, which is dark, dark, which is 10 over 24 times 9 over 23. Now, probability of getting at least 1 dark means you've got 3 different ways you can get that. You can get this way, and that way. So all these 3 different ways you can get at least 1 dark chocolate. So it's going to be 10 out of 24 times 9 over 23 plus 10 out of 24 times 14 over 23 plus 14 over 24 times 10 out of 23. I don't have enough space. I'm going to try to rewrite that so I do have enough space. So it's going to be 10 out of 24 times 9 over 23 plus 10 out of 24 times 14 over 23 plus 14 over 24 times 10 over 23. When we put this into our calculator, we end up getting 9 over 37. Okay, next question. Jean always goes to work by bus or takes a taxi. If one day she goes to work by bus, the probability she goes to work by taxi the next day is 0.4. If one day she goes to work by taxi, the probability she goes to work by bus the next day is 0.4. Given that Jean takes the bus to work on Monday, so bus on Monday, find the probability that she takes a taxi to work on Wednesday. Okay, if she takes the bus on Monday, so the 2 combinations you end up getting is bus and taxi. So if she takes the bus, that means the probability that she goes to work by taxi the next day is 0.4. So taxi would be 0.4. And then that means 1 take 0.4 is 0.6. So the probability of her taking a bus on Tuesday is this. So this is for Tuesday. Now Wednesday, I have to do the same thing again. Bus, taxi, bus, taxi. So this is for Wednesday. Okay, so if she takes a bus, then the probability of her taking a bus taxi again is 0.4. So this part will be 0.6. If one day she goes to work by taxi, the probability she goes to work by bus the next day is 0.7. So that means this part will be 0.7 and 0.3. So we're looking at where she takes a taxi to work on Wednesday. So the only way she can get it is that combination or this combination. So probability taxi on Wednesday is equal to probability of B and then T plus probability T and then T, which is equal to 0.6 times 0.4 plus 0.4 times 0.3, which means we end up with a value of 0.36. On a randomly chosen day, the probability that Bill travels to work by car, by bus, or by train is 0.1, 0.6, and 0.3. So car, bus, and train, 0.1, 0.6, and 0.3. The probabilities of being late when using these methods of travel are 0.55, 0.3, and 0.05. So late and not late, late and not late, late and not late. So late is 0.55, which means not late will be 0.45. Late when he travels by bus is 0.3, so it'll be 0.7 for not late. Late for taxi is 0.05, so not late will be 0.95. B, find the probability that on a random chosen day, Bill travels by train and is late. So probability of train and late is equal to probability of train times probability of late. Probability of train times probability of late given train, which is equal to 0.3 times 0.05, which is 0.015. This is part 1. Part 2, Bill is late, so probability of late. Now there's three different ways you can be late, which is car and late, bus and late, or train and late, which is equal to probability of C and L plus probability of B and L plus probability of T intersect L, which is equal to 0.1 times 0.55 plus 0.6 times 0.3 plus 0.3 times 0.05, which is equal to 0.25. C, given that Bill is late, find the probability that it did not travel by car. So probability of not car given late, which is equal to probability of not car intersect late over probability of late. Not car and late, this can be worked out easily, which is there's two different combinations, which is probability of B and L plus probability of taxi and late. All of our probability of late is, we've already worked it out, which is part 2, probability of late from 2, because we've already worked it out. So bus and late is 0.6 times 0.3 plus taxi and late is 0.3 times 0.05. All of our probability of late, which is 0.25, we've already worked it out from part 2, which gives us a value of 0.78. A box A contains 7 counters, of which 4 are green and 3 are blue. So green is 4 out of 7 and blue is 3 out of 7. And box B contains 5 counters, of which 2 are green, so 2 out of 5, and blue are 3 out of 5. A counter is drawn at random from box A and placed in box B. A second counter is drawn from box A and then placed in box B. A third counter is drawn into box B. So first one is A to B. Second pick is A to B, and third pick is just picked from B. Okay, draw a tree diagram to show this information. Okay, so it's going to be quite big because there's 3 picks. So first thing is obviously from box A, you'll have 2 different combinations, which is green and blue, which is just 4/7 and 3/7. Now, second pick is still from box A, and it's gone down by 1. So it's going to be 3/6, and 3, blue has not changed, so it's 3/6. If you pick a blue first from box A, then the number of greens doesn't change, so it'll be 4/6, and number of blues will be 2/6, it's gone down by 1. Now the third pick is from box B, so green, blue, oops, undo, green, blue, and green, blue. Now remember, we put 2 of these, 2 colors from A into B. So if we pick a green and a green, that means the green number of greens in box B increases by 2. So it'll be 4/7 now, because before it was 5, we added 2 more, so it's 4/7. Now if you still pick a green and a green, the number of blues has not changed, but the number in the box has gone up by 2, so it's 3/7. Now if we pick a green and a blue from box A and put it into box B, then both the green and blue increase by 1, so it's going to be 3/7 and 4/7. If we pick a blue and then a green and then put into box B, then again both the green and blue increase by 1, so it's going to be 3/7 and 4/7. And if you pick a blue and a blue, so then the number of greens stays the same, which is 2/7 in total, but the number of blues goes up by 2, so it's going to be 5/7. Okay, so that's done. Part B. The event C occurs when 2 counters drawn from box A are of the same color. The event D occurs when the counter drawn from box B is blue. Find probability of C. So probability of C, so is when you draw 2 counters from box A that are of the same color. So that means we get green, green, or blue, blue. So it'd be probability of green, green, plus probability of blue, blue, which is equal to 4/7 times 3/6 plus 3/7 times 2/6, which means we end up getting 3/7. So that's B. C, probability of D now. The event D occurs when the counter drawn from box B is blue. So all the different combinations where you get blue. So you can either get blue at the end. So it's probability of G, G, B plus probability, probability of G, B, B plus probability of B, G, B plus probability of B, B, B. So there's all the combinations where blue is right at the end, which is equal to 4/7 times 3/6 times 3/7 plus probability, plus 4/7 times 3/6 times 4/7 plus, so that's one combination, that's a second combination, plus 3/7 times 4/6 times 4/7 plus the last one is 3/7, blue, 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 3/7 times 2/6 times 5/7. So you couldn't see it, it's that one, that one, that one, and that one. Okay, when we put this into a calculator, we end up getting 27/49. Now C done. D is probability of C intersect D. Event, so that means the event that 2 counters drawn from box A are of the same color, it's the same color, and also the last counter is blue. So that means we end up getting probability, so combinations of green, green, and then blue plus probability of blue, blue, blue. So green, green, blue is 4/7 times 3/6 times 3/7 plus 3/7 times 2/6 times 5/7. And we end up getting 11/49 in our calculator. E is find probability of C union D. Okay, because we've got probability of C, probability of D, and probability of C intersect D, so probability of C union D using the addition formula is probability of C plus probability of D minus probability of C intersect D, which is equal to 3/7 from the first part B plus 27/49 from part C minus 11/49, which gives me 37/49. F, given that all three counters drawn are the same color, find the probability that they are green. So F, it means probability of green, 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 given all three are the same. All three same color. Which means it's the same thing as working out probability of green, green, green on top over the only ways you can get all three are the same color is probability of green, green, green plus probability of blue, blue, blue. Now green, green, green is the same thing as 4/7 times 3/6 times 4/7 all over the two combination at the bottom, which is 4/7 times 3/6 times 4/7 plus blue, blue, blue is 3/7 times 2/6 times 5/7. When you put that into your calculator, you get 8/13. The last question I'm going to go through. Mary chooses her outfit based on the weather. The probability that it will be sunny when Mary wakes up is 0.45. So the two combination is sunny and not sunny, 0.45, and then that would be 0.55. Probability that Mary will wear something yellow is 0.7 when it's sunny. So yellow, not yellow. Yellow is 0.7, so not yellow is 0.3. If Mary wears yellow, so when it is sunny, or 0.2 if it isn't. So if it's not sunny, then the chance of her wearing yellow is 0.2, so not yellow is 0.8. And then we've got favorite earrings or not. So if Mary wears yellow, there is a 25% chance that she'll wear her favorite earring. So 0.25 favorite earring, so 0.75 not her favorite earring. But only 10% chance if she is not wearing yellow. So favorite earring is 0.1 if she's not wearing yellow. So not favorite will be 0.9. Not favorite earring is 0.9. And similarly, favorite earring and not favorite earring is 0.25 if she wears yellow, 0.75. And if she's not wearing yellow, it's the same as before, 0.1 chance of wearing a favorite earring, 0.9 chance of it not wearing it. What is the probability that Mary will be wearing yellow today? So yellow, given that she is not wearing her favorite earring. So yellow given not favorite. Using the conditional probability formula, this is probability of Y intersect not favorite earring over probability that she doesn't wear her favorite earring. Now, probability of Y intersect not favorite earring, there's two different combinations, so it's going to be not favorite. So SY, so sunny, yellow, and not favorite, or it's going to be not sunny, yellow, and not favorite. So two different combinations. So it's going to be 0.45 times 0.7 times 0.25 times 0.75, sorry, plus 0.55, so that's one combination, 0.55 times 0.2 times 0.75. Let me just use a different color to highlight the next one. So if I want to show a probability of not favorite earrings, it's those two that I've just highlighted plus this extra one, which is here. Sorry, there's 4 different ones. Undo. So all the way we get not favorite, which is here and that one. So the first one would be 0.45 times 0.7 times 0.75. So the second combination would be 0.45 times 0.3 times 0.9 plus the third combination is, forgot that one, 0.55 times 0.2 times 0.75, and plus the last one is 0.55 times 0.8 times 0.9. When we put this into a calculator, in the top we end up getting 0.31875. In the bottom we end up getting 0.83625. When we divide it, we get 0.3811659193. When you round it, you get 0.3182 to 4 decimal places.